Let's start the first session of this afternoon. And this session is about succinct LWE and evasive LWE. And the first talk is given by Xinyu Mao on random oracle like the primitive from lattice. Okay.
Hey, good afternoon, everyone. Hope you enjoyed your meal. So today I'm Xinyu from University of Southern California, and today I'll be talking about universal computational extractors and multi-bit AIPO from lattice assumptions. And this is joint work with Yilei from Tsinghua University. So our work will be focused on the question of instantiating random oracle. So as you know, many simple and efficient schemes are only secure in the random oracle model. For example, we have many encryption schemes from Fujisaki Okamoto transform, and many proof systems are secure under Fiat-Shamir transform. And we have a similar work by CGH04. They prove that this methodology is unsound in general, meaning that a random oracle is uninstantiable in general. So more specifically, they construct an encryption scheme that is secure in random oracle model, but insecure when the random oracle is replaced by any specific hash function. However, the belief is that these counterexamples are artificially contrived, and when we use the heuristic of instantiating a random oracle by hash function, we still get a secure construction. So to bridge the gap between the practical usefulness and the theoretical unsoundness of random oracle methodology, a natural remedy is as follows. So first, we identify some random oracle-like properties, and which is sufficient for the application in mind. And then we construct hash functions with such properties from well-formed assumptions. So a prominent example is correlation intractable hash function, which is sufficient to instantiate Fiat-Shamir transform. And in this work, we focus on two random oracle-like properties. One is called universal computational extractor, and the other is point obfuscation. So let me introduce them in order. So we're starting from the most direct question. So what is a random oracle-like function look like? So maybe the most direct way is, the most direct formulation is like this. So for any PVT adversary with given the hash key, and it cannot distinguish the two worlds, where in one world it has access to the random oracle, and in the other world it has access to the hash function h. But just a moment of thought will reveal that this is just impossible, because the adversary can distinguish by evaluating the oracle at a single point, say, because it has a hash key, and it can compare the oracle answer to the hash value at that point. So this is too good to be true. So to fix this and get something meaningful, we divide this adversary into a two-stage algorithm. So the first stage, called the source, has access to the oracle, and the second stage, called distinguisher, has the hash key and has to distinguish which world they are in. So, but just splitting into two stages does not help very much, because you can just the source can just send any arbitrary state to the distinguisher, and they just look like one algorithm. So one way to get some meaningful definition is to put some restriction on the sources. Say we say the sources send some message to the distinguisher denoted by L. We call it leakage. So consider the simplest case, where the source only issue one query X to the oracle and get the answer Y. So in this case, we say this source is unpredictable if X is unpredictable given the leakage L, and we say strongly unpredictable if X is unpredictable even given the random answer Y. So so we call the hash function is a UCE if it is. So we say it's one query, and for one query unpredictable sources, if this indistinguishability holds for all unpredictable adversary. So another random oracle-like primitive is point obfuscation. So a point obfuscation is just output a program on input X. It outputs a program that computes the point function at that point. And the security requires that on any input X, the program is indistinguishable from a distribution of null programs. The null programs computes the all zero function. So the more interesting thing about point obfuscation is in the presence of auxiliary input. So we have another auxiliary information which is jointly distributed with X. And we want this indistinguishability to hold even if the distinguisher is given this auxiliary input. So, so basically we want this indistinguishability to hold as long as X is unpredictable given the auxiliary input. And this, we can generalize this point obfuscation to multi-bit point obfuscation, where we obfuscate a more generalized point program. So the program outputs a message M on the point X and outputs, say, a failure symbol on all the other inputs. So we have similar definitions with auxiliary input and unpredictability. So previous constructions of these two primitives are basically all have to be based on I/O. So the approach is given, the constructions given by Braska and Mittelbach use I/O plus AIPO to get both primitives. And we mentioned that UCE in this case will imply another interesting application called polynomial many hardcore bits. It's basically a hardcore function for any one-way function, and we can extract polynomial many bits from any one-way function. So more specifically, the construction looks like this. It's quite simple. So for UCE, BM14 shows that the obfuscation of a puncturable PRF is a UCE. And for multi-bit AIPO, they show that the obfuscation of a very naive program is a multi-bit AIPO. So the program just on input Z, it compares with if Z equals to X, it outputs the message Y, and otherwise outputs some failure symbol. So our results is basically we put forth a new primitive called obliviously programmable function. This is a new abstraction somewhat similar to witness encryption. And we show that in this framework, basically we can replace I/O by OPF. So next we construct OPF from lattice assumptions. These assumptions are sub-exponential LWE and private cone evasive LWE, which I will introduce later. And we mentioned that this construction is similar to the CVW witness encryption by Ilevy, Noid, and Hautek. Yeah, and so this similarity is more interesting to say that all these constructions have connections to witness encryption. So what is obliviously programmable function? So this is a keyed function which has a key generation algorithm called program. So the program algorithm takes as input a circuit from some circuit class C and a value Y star from some domain and produce a programmed key. So for correctness, we want to say if the circuit C computes some point function at some point X star, then when we evaluate the function with the programmed key at the programmed point X star, we will get the programmed value Y star. And for security, we require two properties. The first is privacy. It says that the programmed key will computationally hide the circuit as long as the circuit is indeed a point function or it computes all zero function. And the programmed value Y is chosen uniformly at random. And another property is if we are programming on the all zero function, so if C computes the all zero function, then the value Y star does not matter at all. Basically, we say the programmed key computationally hides Y star. So given this definition, we use UCE as an example. So we have a very simple construction from OPF to UCE. Basically, the UCE hash function is the OPF function, and the key generation is just a program on the all zero function at say value 0. Actually, the value 0 does not matter at all. It can be any other value because we have the value hiding property. It's the same thing. So, the our theory says that if we have OPF support which supports some circuit family C, and we have AIPO in that circuit family, then this function H, hash function H is a UCE. So next we present a lattice-based OPF construction, which is based on GGH15 coding. So in GGH15 coding, circuits are represented as a matrix branching program. So a matrix branching program consists of a vector V and a bunch of matrices, M matrices. And to evaluate on our input X, we select a subset of M matrices according to X. And then we multiply the vector V with the product of M matrices. And if this vector product equal to 0, we say the branching program outputs 1, so or it accepts the input X, otherwise it rejects or outputs 0. So the GGH15 coding is that given such a matrix branching program, we first construct some S hat matrices. So this matrices has 2 tracks. The first track is identity matrix, and the second track is the branching program M matrices tensored with some short random matrices. And then the encoding is produced by sampling uniform A matrices, A1 through AH, and use along with trapdoor, and we use a trapdoor to do some Gaussian pre-image sampling. And what's the point of doing this is the functionality of such encoding is that given the encodings, we can approximately compute the value of S hat sub X, which means it's the product of S selected by X and the AH, which is the final A matrices. And the security says that encodings are pseudo-random, which means it hides the branching program. So given the encodings, a natural construction of OPF look like this. So we take the program, the key to be simply the encodings of the circuit, the branching program. And the value is simply the approximation of S hat X AH given by the encodings. So the question is, how can we program the value at X star? So this is done by the so identity matrices we add in the first track. So in the previous works of GGH15 coding, we don't have such a track. So by adding this track, by direct calculation, we see that the value at the point X can equal to the value of the top rows of the AH, the last A matrices, the last A matrix, and plus some value controlled by the branching program. And if the branching program equals to, if the branching program accepts X star, means that V times M X star equal to 0, then the value will equal to, or roughly equal to, the top rows of AH. So by doing this, we can program the value at X star by controlling the value of the top rows of AH. So this concludes the programming functionality. So for security, we have to prove these encodings are indeed pseudo-random and hence hide the circuits. So this is done by evasive LWE. So to encode this, to prove the pseudo-randomness, we just relying on LWE to show it suffices to show so the evaluated products are pseudo-random. And again, by calculation, we can say the each of the products looks like top rows of the last matrices plus something controlled by the branching program. And the blue, we have a blue part which is pseudo-random because it is basically a lattice-based PRF. And finally, we see that if this branching program really computes a point function, we get the pseudo-randomness, because at that point, for that point, we have the value is randomized by the top rows of H, and for the other point, the value is randomized by the blue part, which is a lattice PRF. So this is exactly the privacy property we want for the PRF. So to summarize, first we have constructed the OPF from GGH15 coding, and its security is proven under sub-exponential LWE and evasive LWE. And branching programs can support the family of NC1. And combined with our OPF-based construction of UCE and the multi-bit IPO, we get UCE and the multi-bit IPO from the some lattice assumptions and the existence of AIPO in the NC1. Supported the NC1 is supported family for our OPF. Okay, so a few questions. So can we program for all circuits, because now we can only support NC1, or can we program more points so that we have more applications? So the second one is, can we base the security on standard LWE? But I think to do this, we have to first prove CVW witness encryption under standard LWE. So finally, can we use our OPF to do more, to instantiate other to instantiate RO in other settings like full domain hash signatures? Yeah. And we highlight that private coin evasive LWE in the current situation is more of a heuristic and unstable situation. Yeah, thank you.
Okay, thanks for the talk. Any questions?
You need private coin, but not public coin, evasive LWE?
I think basically the reason is that we use the same proof strategy as the CVW witness encryption, and in that proof, we need to use some private coin to generate some noise, which cannot be published to the adversary.
So are your construction immune to the attacks known in, I say, Eurocrypt 24?
Yeah, I think general private coin, basically LWE is not known to be secure, but we can assume it holds for the specific sampler we used. Yeah.
Okay, thank you.
Thank you.
Any other questions? Okay, I have a question. For some lattice trapdoor-based scheme, the security is usually based on this problem.
Yeah.
But I see your slides. You already mentioned the LWE family assumptions.
I think we're just using the trapdoor sampling, which I think you can. Yeah.
So you don't need to rely on these, right?
Yeah, I think LWE will suffice. Yeah.
Okay, thanks. Okay, thanks again. And the second talk is given by Valerio Cini, and his talk is about ABE from evasive LWE.
So thanks for the introduction. So I'll be talking about the ABE for Turing machine from circular evasive LWE, and this is a joint work with Hatakui from NTD Research. So let me start by defining what ABE is. So ABE stands for attribute-based encryption, and is a generalization of the standard public key encryption that allows for a more fine-grained access control to the messages encrypted in the ciphertext. So the syntax is the following. There is a setup algorithm that takes as input a security parameter and some class description f. So this class description you can think of as a class of algorithms that are going to parameterize the construction. So for example, you can take f to be the class of arithmetic circuits. But more generally, we would like to even allow for a uniform model of computation, so allow for algorithms that can work on arbitrary input. And in this work, we do so by setting the class F to be the class of Turing machines. So for this class, the syntax is the following. So the setup is going to output a master public key and a master secret key. With the master public key, you can run the encryption algorithm and input some message, an attribute X that you can think of as the input of the Turing machine, and some time bounty. With the master secret key, you can run the key generation and input the description of some Turing machine in the class to obtain an associated secret key. And then with these two components, you can run the decryption, and you're supposed to recover the message whenever m of xt equals to 0, which we mean that you run the Turing machine on input x for time t, and then you look, for example, at the first bit of the work tape of the Turing machine. So what do we know about ABE for Turing machine? So the state-of-the-art construction is a work from last year by Agrawal, Kumari, Yamada, with the following efficiency metric. So they obtain a construction where the ciphertext is quadratic in the running time bound. The secret key is quadratic in the description of the Turing machine. And the security is obtained by assuming the circular evasive LWE and the tensor LWE assumption. So what we do in this work is improve along all the three metrics. So in particular for ciphertext, we obtain linear size ciphertext in the time bound, and the same works for the encryption running time. The secret key are a constant size, and what depends on the description of the Turing machine is only the key generation running time. And then we remove the need for the tensor LWE assumption. And the way we achieve this is by introducing a new notion of encodings and techniques to recode different kind of encodings. So let me go into details about this part. So in the similar construction of Bonnet et al. Of AB for circuits from LWE, there was this notion of encodings that I'm going to refer to as the BGG encoding, which have the following structure. So to encode some bit string of length L, you're going to use a matrix A of, again, length L, and a single secret S. So for each bit of the encoding, you're going to use one block of this matrix, and you're going to reuse the same secret S across all the different bits. So what they show is that this kind of encoding allow you to perform homomorphic evaluation on the encoded attribute. So in particular, given the encoding of Z, you can compute the encoding of f of Z for any circuit F. The drawback of this kind of encoding is that the size of the public parameter, so the size of this matrix A, is linear in the size of the attribute that you want to encode. In this work, we introduce this dual notion that we refer to as the dual encodings, where we kind of switch the role of A and S. So the description of this encoding will be something like this, where you're going now to use the same matrix A across all the different bits that you want to encode. And what changes is the secret that you're going to use. So you have fresh secrets for each bit. And the properties that we get is that now the description of the public parameter is constant, so independent of the length of the attribute that you want to encode. And the drawback is that now you cannot perform any kind of operation. So you can only do projection. So you can take the encoding of some substrings of Z. So what we are going to do is leverage the orthogonal properties of these two encoding to construct our construction, basically. So in like overview is that we are going to use the dual encoding to encode the work tape of the Turing machine, which is very long. And then we're going to use the BGG encoding to do the local operation of the transition function of the Turing machine. So what we need is now a way to switch between these two kind of encodings in a way to allow these kind of properties. So now I'm going to present how you do this for the dual encoding. So you want to go from a dual encoding of Z under some secret S and some matrix A0 to a dual encoding of the same attribute under a new secret and new matrix. So what we need to do this is the following quantities. So you will need two matrices, C and C prime, that you can think of as the encryption under the matrix B and the matrix W, LW encryption. And then a matrix K, which by this notation, I mean that is a short preimage under the matrix B of the expression in the parentheses. So how can you parse this expression? So the matrices B and W will be part of the master public key of the scheme. The matrices C and C prime will be part of the ciphertext of the construction. And the matrix K will be part of the secret key that you give out. So what property does this encoding achieve next to correctness, let's say? So the size of the ciphertext component is linear in the attribute that you want to encode. and it also depends on the secrets that you are switching from and to. And whereas the secret key component is constant in size, so it does not depend on the length of the attribute that you are encoding. Okay, and in general, we show that you can do a similar result for all kind of possible encoding. So from dual to dual, which is on this slide, from BGG to dual, and from dual to BGG. And the properties that you achieve are the same. So you have a ciphertext component whose size is linear in the attribute, and a key component of constant size. Okay, so now let me use this to show you construct a AB for Turing machine. So we are going to actually construct AB for this modular computation that we call the iterated computation. And then I'm going to describe how you get to ABE for Turing machines. So in this modular computation, you have 3 parameters, locality L, space S, and time T. So you're applying this function that goes from L bits to L bits iteratively T times. Okay, and it's parameterized, this computation is parameterized by 2 functions, read and write, that tell you at each time what kind of subset of the work tape you're reading and writing on. And the parameter range is the following. So L is much shorter than both the workspace and the time bound. So at time t, we define ZT to be the work tape of the machine. And the evolution of the work tape across time is the following. So you start with a work tape where you have your input Z padded with 0 to fill up the work tape. And then you compute this function iteratively in the following way. So this notation is the following. So for the substring associated with the subset outside of the right of T set, you're just gonna keep the work tape as it was before. So where you don't write, the work tape stays unchanged. And for the subset where you write, you just apply the function on the subset of the work tape at the time before associated with the read T subset. Okay, you do this till you reach the time bound T. And this is our model. So how can you get AB for Turing machine if you give an AB for this kind of model? Then this actually captures oblivious Turing machines, where the transition functions does not depend on the time that you had. And the total state of the Turing machine that you can support is 2 to the L-1. So the first L-1 bit of the input and output of F will define the state. And then given a compiler from the 70s, this gives you, it can be bootstrapped to an arbitrary Turing machine with a small overhead. Okay, so let's describe now the AB for iterated computation. So we are going to describe it through the lens of the decryption invariant of our construction. So at each point of time, we will have the decryptor will compute a dual encoding of the work tape of the Turing machine of the machine at that point in time under some secret ST. So in the construction, you have a bunch of secrets, S0 to S capital T, which will be associated to the ciphertext, and then a matrix A0, which will be part of the given in the key. Okay. So the first construction that we're going to present is a warm-up construction where all the secret ST are independent from each other. And this will give us a secure construction, but where the size of the ciphertext is quadratic. Then we want to improve on the efficiency of this construction. And the first attempt will be to set all the secret S to be the same. This will give us a linear size construction, but which is insecure. And then we are going to argue how can you refresh the secrets across time so that you still achieve a linear size ciphertext, but you can prove the scheme secure. Okay, so let's start with the warm-up. So I'm going to describe one single step of the computation and describe how this decryption invariant is computed on in this time step. So you start with the decryption invariant time t-1, which is a dual encoding of the work tape at time t-1, and you want to get a dual encoding of the work tape at time t under the new secret. So what you start by doing is you split the work tape in the read part, on which you're going to perform some computation, and the part that is unchanged, so this not write part. So, and then from the left-hand side, you want to get the dual encoding of the right part, and from the right-hand side, you want to get the dual encoding of the not right part. Okay, so let's start with the left-hand side. So we have a dual encoding. We cannot perform any computation. So to perform the computation, we first have to switch to a BGG encoding. So this is what we do. We switch from a dual encoding to a BGG encoding of the same attribute under some secret ST-1 and some matrix D. Once we have a BGG encoding, we can perform the computation. So we apply the function f to this attribute zt minus 1 of read of t to obtain zt of write of t by definition of the iterated computation. And now that we have a BGG encoding of what we want, we need to switch it back to the dual encoding. So we go back to the dual encoding of the same attribute. On the right-hand side, instead, we just need to switch the secret without performing any computation on the attribute. So we do a dual-to-dual recoding, switching the secret from st-1 to st. Okay, so let me describe what is going on. So on the left-hand side, there is a computation on an attribute of size L, which is the locality of the function. You have you do two recodings, one from dual to BGG and one from BGG to dual, and one BGG evaluation to apply the function f. So the overhead from the left-hand side is in the ciphertext, linear in the size of L, of the attribute that you are performing computation on, and the secret key components that you need to add is constant. On the right-hand side, you're doing a recoding on an attribute of size s minus L. So you're going to pay ciphertext size linear in s minus L. Okay, and then this is for one single step of the computation. So across the multiple step, what you get is that the ciphertext size, the overall ciphertext size is s times t. So you pay the same price for each computation step. And for the secret key, this remains constant because you can reuse the key across the different computational steps that you perform, since they do not depend on the secret that you're going to use, but only on the matrices. Okay, so how can we improve the efficiency of this construction? So we could try to set all the secret S to be the same, so that on the right-hand side, we wouldn't have to perform any recoding. So the problem is that this would trivially lead to a broken construction. So for example, at time 0 and 1, you would compute an encoding of some possible different work tape under the same secret and same matrix. And this would lead to a leakage of information about the secret S0. So what we show, and what's the goal, is to find some kind of subsets where you need to refresh the secrets across time. So the secret at time t would be the same as the secret at time t minus 1, except for some subset of the rows defined by these sets u of t, where you would need to refresh the secret. And for efficiency, we need that this subset has small size. In particular, it could depend on the locality of the function. And what we show in the work is that you can take these sets u of t to be exactly the union of the set write of t and the set read of t. Okay, so how does the scheme gets modified? So when we do the computation, it remains unchanged. So what changes is only the right branch that I showed before. So before we were just doing a dual-to-dual recoding to switch the secret, the full secret, across all the entries of the encoding. What we do now is we divide this encoding into two chunks. So the left branch corresponds to the part of the not write of t that intersects the sets where you want to switch the secret. And this here you have to switch the secrets. So you do a dual-to-dual recoding. And on the right branch, we don't need to do anything since the secret can stay the same. Okay. Then you merge and you obtain the encoding that you want. So again, what you have is that you're doing one single recoding, and now the attributes, the length of the attribute on which you're doing the recoding is a subset of the read of t set. So the length of this subset will be strictly less than L. And for this, you pay in ciphertext size a big O of L. And as before, for the secret key, you pay a constant additive overhead. So in total, across all the computational steps, what you pay for the ciphertext is big O of S for the initial secrets, and then L for each computational step. So in total, this is linear in T. And for the secret key size, you still have constant size. Okay. So what it remains is to discuss about the security. I'm going to briefly sketch. So you could try to prove the security of this scheme under the evasive LWE assumption. And to do that, you basically will need to show that the object that you compute with the decryption ups to the random jointly. And this you can do possibly under the LWE assumption. So what I didn't actually mention in the previous construction is that there are some error terms that accumulate when you do computation. And to handle these error terms, we rely on previous techniques introduced in the work of HLL23. And since we rely on these kind of techniques, we also need to rely on their security assumption. So instead of the standard evasive LWE assumption, we need to rely on the circular secure evasive LWE assumption. And for this, we need to slightly modify the construction and add some circular encryption for each time step. So basically, at each time step, you would do some bootstrapping to reduce the magnitude of the noise that you have accumulated so far. And this does not affect the efficiency of the construction, since you still pay OL for each of the time steps. Okay, so to conclude, we showed in our work that we introduced this notion of new encoding with some properties and showed that you can have techniques to recode between these different encodings. Show how you can obtain ABE for Turing machines with better efficiency, exploiting these properties. And as an open question, one would be clearly to kind of try to improve on the assumption, since there has been a recent counterexample to the assumption in the HLL work. And second, trying to find other application for this new notion of encodings and techniques to recode. Thanks.
Any questions? Okay, I have a question. You just mentioned there is a recent work proposed some counter example for evasive LWE.
Yes.
Yeah. Yes. And does that example affect the security of your construction?
So my understanding is that the counterexample, I mean, it affects the assumption. Yeah. It doesn't directly break the construction. So one could try to either like modify the counterexample to break the construction, or find a different assumption that still allows you to prove the security of the scheme while avoiding the counterexample in this recent work.
Okay, thanks. Any question? Okay.
Sorry.
Okay, thanks again. Thanks. And the last talk in this session is given by Hotek Wee and on ABE from Succinct LWE. Okay.
All right, thank you. So I'll be talking about almost optimal ABE for circuits from lattices. So quick recap about ABE, or attribute-based encryption. So again, here we have ciphertext associated with attribute X and a message mu. And secret keys are associated with functions, and the encryption should recover the message mu if f of X is true, and otherwise mu should be hidden. And this should be the case if you have collusions with multiple secret keys. So about a decade ago, we had the first construction of KP-ABE, key policy ABE for circuits, from the standard LWE assumption. In this work, we'll also be looking at ciphertext policy ABE, or CP-ABE, where functions are associated with ciphertext and secret keys are associated with attributes X. So in general, CP-ABE is a much harder problem. It was only a couple of years ago that we had the first construction of CP-ABE for circuits under non-standard variants of the LWE assumption. So in this work, we present new constructions of KP and CP-ABE schemes for circuits from lattices. Our constructions achieve very good parameters. Master public key size, ciphertext size, and secret key size are independent of the circuit size and the length of the attribute. So it's constant up to polynomial security parameter, up to polynomial factors in circuit depth and security parameter. In fact, our parameter sizes are almost optimal up to the dependency on circuit depth. Our results are, and we built these schemes based on the Succinct LWE assumption, which is a falsifiable, which is a non-standard but falsifiable variant of the LWE assumption introduced at my work at Crypto last year. So this new work is actually a pretty big improvement over prior works. In particular, for the setting of KP-ABE, we improve upon the parameter sizes of both of the schemes in the prior work. For CP-ABE, the improvement is even bigger. We improve on the parameter sizes, the assumptions, and the security notions achieved in prior works. So in this work, I'm going to first start with a quick recap of the KPABE from the last crypto, which has a large master public key. And then I'll explain how to reduce the size of a master public key to constant. After that, I'll explain how to extend these techniques from the KPABE setting to the CPABE setting. Before that, let me first tell you about the Succinct LWE assumption. So in this assumption, we have LWE matrix B of dimensions n by q, with dimension n by m, where m is n log q. In addition, we sample L matrices, W1 up to WL, and we arrange all these matrices into a huge matrix, which is the one shown on the slide. And we compute a random gadget trapdoor for this matrix, which is the expression shown on the slide. And the Succinct LWE assumption says that SB plus E remains pseudo-random given all of these additional matrices. So what do we know about Succinct LWE? In general, it's sort of like a Q-type assumption in pairings, where the assumption gets stronger as L increases. However, the assumption is still weaker than the evasive LWE assumption. In this work, I'm going to use PP sub L to denote all of the public matrices. And let me just say that for the rest of the talk, the exact structure of this public matrices are not relevant. All right, so the starting points, we observed that in the prior KPABE for circuits, the main technical building block of the new construction is actually a so-called vector commitment scheme. All right. By vector commitment scheme, I mean the following. There's no binding and no hiding, but just the following syntax. We have a commitment algorithm that takes as input a very long vector x, which corresponds to the attribute in KPABE, and produce a commitment, which is a small matrix of dimension n by q. Right. Moreover, we have additional algorithm, an opening algorithm, that takes as input x and produces a matrix Z that relates the commitment to x tensor G via the following equation. On the right-hand side, we'll have an additional matrix B, which is sort of the same B as in Succinct LWE. The matrix Z is going to be low norm and very wide. And we also have an additional matrix B that does not depend on x, also very wide and low norm, such that C times V is x tensor G minus B times the opening. For the rest of this talk, it's extremely important that you remember this equation. So in the prior work, they gave a construction of such a vector commitment scheme where there's a CRS, where in the CRS, we put in the public parameters for the Succinct LWE assumption. Then combining, I want to say that this previous construction, the details are irrelevant for this talk again. I do want to say that it's a simple construction and the whole thing fits into one line. Then combining this vector commitment with the standard BGG plus type techniques for KPABE, we get a KPABE for circuits with a large master public key, which corresponds to this PP sub L, but with small ciphertext and small keys. All right. So in this work, we built a new vector commitment where the CRS is very small. It's just PP of 2m squared. Remember, m is essentially constant, so we reduce this PP sub L to PP of 2m squared. All right. Now plugging into the previous framework, we immediately get our KPABE with small master public key. Okay. To build this vector commitment, we're going to start by constructing a more general version of a vector commitment, what we call a matrix commitment. We want a way to commit to matrices. What does this mean? I give you a matrix that's very wide, of height n, and I want to produce a commitment like before, which is a small matrix of dimension n by q. And I want also a way to compute openings that satisfy an analogous opening relation from before, except I have x, instead of x tensor G, I have m. Okay? So C times V is m minus B times the opening. Why do I want to work with matrices instead? But before, let me first say that in the construction, we gave a construction of matrix commitment where the CRS is just PP of 2m squared. All right? And then by replacing m with x tensor G, this matrix commitment gives us our vector commitment. So what's the advantage of working with matrices and vectors? Is that with working with matrices, there's a very natural Merkle-style recursion that you can use to construct such a scheme. In this recursion, in the base case, we're going to work with matrices of width 2m. Why 2m will be clear during the recursive step. Okay? So now we want to show you how to commit to a matrix of width 2m. We start by computing the bit decomposition of this matrix as a row vector. So this is going to be a 0, 1 vector of length 2m squared. And then we'll apply the previous vector commitment to commit to this vector of length 2m squared. And this is where the pp of 2m squared comes in. Comes from the previous vector commitment for length 2m squared. All right. So how does the opening work? I need to show you how to translate openings for the vector commitment to an opening for the matrix commitment. And the key is to just show you how to go from bits of m tensor G to m. And turns out there's a way to relate the two quantities by multiplying by a low norm matrix. So by applying the same low norm, applying the same linear transformation to the openings for the vector commitment, you get the opening for our vector commitment. Now, in the recursive step, we're going to think about our matrix as comprising two submatrices, each of width L over 2. All right. To commit to this matrix, I'm going to first commit to each of the submatrices, which have width L over 2, to obtain two commitments of dimensions n by m. Then I'm going to concatenate both of these matrices, and, which gives me a matrix of width 2m, and then commit to this using the commitment from our base case. That's where the 2m comes in. All right, and that's our commitment scheme, which has dimension n by m. All right, that's our new commitment. And how does the openings work? Well, the idea is that we're going to start with the openings for C, C0, and C1, and look at the opening relations. And essentially, we can cancel out C0 and C1 to derive an opening relation for M0, M1. And the expression is going to look like this. You just have to trust me that the algebra works out. Okay? And that pretty much completes our entire KPABE, this entire construction. And now I want to show you how to go from, to get to the CPABE setting. Via the same framework, to get a CPABE, it's sufficient to give a commitment scheme for circuits. What does a commitment scheme for circuit means? I want a way to, given a big circuit, compute a commitment, which is a small matrix of dimension n by m. And later on, there's a notion of opening. And now the open algorithm is given an input to circuits, together with a value x, which you can think of as the input to the circuit f. And the opening relates the commitment to f of x via an equation that's analogous to the one from before. C times v sub x equals f of x minus v times the opening. Here now the V matrix will now depend on x, but it will not depend on f. Okay? Now given such a commitment scheme for circuits, you can actually plug into the previous framework from before, and that gives you the almost optimal CPABE. So the PP of 2m squared goes into MPK, C sub f goes into ciphertext, and V sub x goes into secret key. All right. So now, how do we construct such a commitment scheme for circuits? To handle commitments to general circuits, it suffices to handle input gates, addition gates, and multiplication gates. So it turns out input gates and multiplication gate, input gates and addition gates are quite simple. It follows quite readily from standard techniques. So the main technical challenge here is to handle multiplication gates. So first, let me start by saying that the naive approach of doing BGG plus style homomorphic multiplication doesn't work. And basically, the problem is that there's an extra V matrix hanging around. Instead, what you can do is to apply a BGG plus homomorphic multiplication to C times V, so the expression on the left-hand side. It gives you something pretty close to what we need. In fact, on the right-hand side, you get exactly what we want, except the left-hand side is not of the form C sub f times V sub x. Okay. However, turns out you can do a little bit of algebraic manipulation. I try to figure out whether the timer is counting up or counting down. So, okay. All right, you can do a bit of algebraic manipulation and rewrite the expression on the left as a product of a very wide matrix of width m cubed that depends only on the c's, and a matrix that depends on the z, only on the x. Okay. Now the second matrix becomes a little bit more complicated, but that's not too bad. Basically, we need to relax the requirement so that v sub x is allowed to depend on the depth of the circuit. Okay. The bigger problem here is that the matrix, the first term in this product, has width m cubed, and we really want a commitment of width m. So what do? We take our matrix commitment and commit to this matrix of width m cubed, and then you get to a matrix of width m. So this almost works, except you're going to get noise growth that's doubly exponential in circuit depth instead of singly exponential. To solve that problem, you just need to throw in an extra gadget matrix and then do the usual noise reduction. Okay. All right. To conclude, we present new ABE schemes for circuits from the 2m squared succinct LWE assumption. I want to highlight the two particular corollaries of this work. The first is the first optimal broadcast encryption scheme from a falsifiable assumption. Another is that actually it follows from our work that 2m squared succinct LWE implies hardness of L succinct LWE for large L. Okay. So L succinct LWE isn't like your Q-type assumption in pairings. The hardness doesn't increase indefinitely as L increases, but rather plateaus at 2m squared. I want to also take this opportunity to highlight a concurrent work that uses some of the similar ideas from our KP-ABE together with some really new cool techniques to get an almost optimal LFE for circuits from the standard LWE assumption. This will be appearing at Stock, so please keep a lookout. All right, so I want to just conclude with a little story. So, many years ago, I was a PhD student, and one of my friends won a teaching award. So I was curious, teaching is hard, so I asked him, what's your secret? And he said the secret is to dress well, so that the girls will like you, and the boys will want to be like you. So I mentioned this to my PhD advisor, Luca Trevisan, and he said, that's a complexity theory approach for hard problems. So interestingly, in this work, I actually started out with a hard problem, but not so hard, and actually ended up applying the complexity theories approach to get to the final results. So I want to dedicate this work to Luca Trevisan, to thank him for his wisdom, his kindness, his humor, and his friendship. And I miss him very much. Thank you.
Any questions?
Hello, Hotek. Do you think is there any common points between your work and the last presentation? I mean, is it possible to use both your technique and the technique of the last presentation to build a KP or CP ABE for Turing machines from Succinct or Evasive LWE?
Right, that's a very good question. So one thing to keep in mind is that, in general, there are two orthogonal issues. One is that's the circuit depth issue, and we don't get improvement on circuit depth. In general, if you want to solve the problem of AB for Turing machines actually correspond to computation with extremely large depth. So you inherently have to deal with the issue of noise reduction. However, it does seem like you can use some of these techniques to at least get a scheme for Turing machine with smaller ciphertext. And in fact, something like this was done in a follow-up work by the same people who did the concurrent work that I mentioned. But they still require some sort of secure evasive LWE. So in the setting where there's some sort of where you want constructions that independent on circuit depth, in that regime, we don't really know techniques to get security from non-falsifiable assumptions. Sorry, and constructions from falsifiable assumptions.
Any other questions? Okay, coffee break.